This is the FPGA Accelerated Audio Pitch Detection using High-Level Synthesis project by Daniela Michalka, George Madoff, Grace Tang, and Rachel Yan. So a little bit about an overview. For this project, we implemented a fast Fourier transform, or FFT, on an FPGA. The FFT converts a signal from the time domain into the frequency domain, which lets us see what frequencies are present in the signal and their amplitudes. We implemented two versions of the FFT, a baseline design and an optimized design. The optimized version uses pipelining, parallelism, and resource level optimizations to improve throughput and latency. Comparing the two allowed us to quantify performance gains and understand the trade-offs between speed, area, and resource utilization. We then used the FFT output to identify music notes in the wave files, demonstrating a practical application for the design, which is real-time frequency analysis and pitch detection.
For our project, we're basing our optimizations off of a paper from UCLA, which details the design of a general high-performance FFT generator using HLS. This paper focuses on the Cooley-Tukey algorithm, which works by recursively splitting a DFT of size n into two smaller interleaved DFTs of size n over 2. This results in an overall O n log n complexity. At its core, it performs a series of butterfly operations, abbreviated BF, on a pair of data points, and it consists of three nested loops. Its outermost loop, the stage level, is fixed at log 2n iterations, and this level computes the number of group and pair level iterations. Ng, the number of group level iterations, doubles with each stage, and Np, the number of pair level iterations, halves with each stage, such that Ng times Np is equal to n, and it's assumed that n is a power of 2. Next is the group level loop, which consists of ng iterations, and all group level butterfly operators share the same twiddle factor, shown as TW. After that is the pair level loop, which consists of np iterations. This loop calculates the two indices for the butterfly operator, and then it performs the butterfly operator on those two indices. In addition to this, it's also common to process the input with a bit reversal. In order for more efficient memory usage, the FFT can perform in-place computations, and in order for the output to be in order, the input must be bit reversed. The paper specifically focuses on creating an optimized version of this Cooley-Tukey algorithm, and the biggest challenge it aims to address is the dynamic loop bounds in the group and pair loops. Because these are determined by the stage iteration, unrolling and pipelining them is difficult, and this also results in unpredictable data accesses, which also makes array partitioning difficult. The paper solution is to enforce a constant unrolling factor across the group and pair level loops. In order to distribute the parallelism between the two loops, the paper proposes the following strategy. If ng, the number of group iterations, is less than a set unrolling factor uf, then we would pipeline at the pair level with unrolling factor uf. Otherwise, if ng is greater than uf, we would want to pipeline at a group level with unrolling factor uf over ng. By using this strategy, not only can we pipeline and unroll efficiently, but it also allows for a cyclic partition with factor uf. And in order to optimize the memory access pattern for this, the group and pair level loops are swapped. The biggest design consideration here is the UF that we select. A higher UF means more parallelism, and thus a lower latency. However, resource utilization increases significantly with UF, so we need to find a balance. The paper details the performance for examples going up to UF equals 32, shown on the right. And based on the ECE Linux synth report, we have the following resources on this Z-board. As a result, based on these early estimations, a UF of 2 or 4 seems feasible, and this still allows for a 20 to 30 times speedup.
Now I will go over how our group implemented the project. The main component of our application includes the FFT algorithm, which is the core of the program, a wave file reading functionality, and a note detection logic. The two additional functionalities were added as we wanted the program to be more application-like and have connections to the real-world scenarios. First, for the FFT core algorithm, we used the standard Cooley-Tukey FFT, which we already introduced earlier, so I won't go into details in here. One thing to note is that for the twiddle table that we implemented, we pre-computed all the required values so that we don't have to do complicated math in the twiddle table during the program. In our design, we also used n equals to 1024, which gives us a good balance between resolution and the hardware resource usage. If the number is too small, there isn't going to be enough samples for note detection, and if the number is too big, that will be too much resources on the hardware. Next, for note detection, we first apply a hand window. This is a functionality that helps to smooth the audio frame and reduces spectral leakage, which makes the FFT output much cleaner. After getting the FFT result, we look for the bin with the highest energy. Because musical notes tend to show up as many different peaks in the spectrum, and as the picture shown on the side, so this is an example of an A4 note, and there are a few peaks in there, but only the largest and most dominant peaks marks 440 Hz. So this is what we're looking for, and that is marked in the red line. And we basically use that functionality to transform to the correct note we want. So using the dominant frequency, we map it to the closest musical note using a lookup table that spans all 8 octaves. Finally, our WAV file reader is responsible for getting the audio data into a format FFT can use. We parse the WAV file, pull out the audio samples, and then convert them into normalized floating point values between -1 and 1. This is the format our FFT expects, and it ensures that different recordings with different volume levels can all be analyzed consistently.
So our main optimization was implementing the unrolling, pipelining, and array partitioning pragmas used by the paper. To make this work, we swapped the group and pair level loops and added if-else logic to compare UF to NG, and thus unrolling the corresponding group or unrolling at a group level or a pair level, depending on this comparison. An issue we faced with this, however, was with the pragmas. Because the unrolling factor used in the pragma must be known at compile time, having it depend on the stage iteration became an issue since the stage iteration varies with every loop. Our solution to this was to break the stage level loop out into function templates and then to call each stage level iteration individually as shown. However, a drawback of this is that we have to use a fixed FFT size n. Since all of our inputs are size 1024, we were able to do this by just calling the stage function 10 times. Another smaller optimization we implemented was to use a sine and cosine table instead of computing these values when initializing the twiddle values. This was a more minor improvement since it was outside of the main FFT loop, but it also did reduce DSP usage a bit, and it also but as a downside, it increased the memory usage needed to store the array. A further step we tried to do was to implement a twiddle table instead of having separate sine and cosine tables, and this also improved memory usage slightly since we were storing one table instead of two, in addition to a slight decrease in latency. It also improved precision slightly since we had less values that were rounded. And then lastly, the other major optimization was finding an unrolling factor that doesn't exceed memory usage. And this was tested using csynth.
We created 2 test files to test our design. In one of the test files, we created a synthetic signal. We chose 440 Hz to be an input into our FFT. The FFT then outputted all the bins with all the corresponding frequencies. As you can see, the frequencies are pretty close to 440 Hz, ensuring that our FFT design worked. We then also created another test bench to input WAV files. Each WAV file had an instrument playing a single note. We then had that WAV file inputted into a floating point conversion function that created floating point samples, and then those floating point samples went through a Hahn window to then be an input into our FFT DUT. Our FFT DUT then computed the frequencies for the samples, and then we generated the max amplitude frequency and converted that into the corresponding note. Lastly, we checked if that note was correct with what we expected from the WAV file, and then outputted that into the terminal. Something to note is that originally we had a hard time generating the correct note, and this was due to starting at the beginning of the WAV file, where there was a bit of noise, and the max frequency wasn't the corresponding note, so it is important to start somewhere either in the middle of the WAV file or somewhere kind of off from the original start. And as you can see, our test results are pretty accurate. Almost all the time we were able to detect the correct note. Occasionally we would get a fail, but it would be pretty close. As you can see with D2 and F2, they're in the same octave, just slightly off in frequency. And I would consider this a very big success, given that our design used a table and we couldn't generate sine and cosine precisely.
In this section, we explored trade-offs of the FPGA implementations and co-simulations across 4 designs: the baseline and the optimized versions with an unroll factor of 2, 4, and 8. When observing the resource usage, we see a clear trend. As the unroll factor increases, so does the utilization of all major resources: DRAM, DSPs, flip-flops, and LUTs. Despite this increase in hardware utilization, the latency improves dramatically. The baseline design takes 98,477 cycles, whereas with an unroll factor of 8 design completes in about 4,394 cycles, a decrease in latency by a factor of 22.41. Our target devices are the Z boards that were utilized throughout the HLS course, and ultimately we could see that by using an unroll factor of 8, it utilizes more LUTs than accessible, exceeding the limit by approximately 27%. In turn, our final design uses the unroll factor of 8, resulting in a latency reduction by about 17.52 times. In the next few days, we aim to explore further optimizations that can result in a speedup of 30 times or more. And with that, we'd like to show a demo of our FFT program utilizing the optimized version on the FPGA, displaying the output of the DUT. Also, we'd like to show a comparison of a frequency in using a program called Beep within the console to demonstrate that our WAV files are playing the same frequency as what we would expect. And with that, let me pull up our code and I'll log into the FPGA.
we already compiled our auxiliary demo.bit file into the SD card of the FPGA, and we'll be running our optimized version. And with that, I'd like to show that we're using 7 of the audio files here, just using A4, C3, D2, D5, E1, F3, and G5. And we can see that our DUT from the FPGA running the simulation has output what wave file we're using, the expected frequency that we have from the note, as well as the detected note frequency and the detected frequency, the detected note. We passed 5 out of the 7 cases. This could be increased if we were to increase our N variable, but we wanted a fair comparison of our version compared to the paper version. And with that, I'd like to show the audio files that we're using, a .wave file using GarageBand. Then this is A4. And then this is, as you've seen here, A4 runs at 440 or 430 frequency. So let me run 430. And I'll play them side by side. Now let me run D5. D5 uses, we can see here, 602. And you see it's higher than A4. And then we have F3. And the F3 we could see is 172. And lower. And with that, we'd like to thank you for listening to our project and hearing about our optimizations. Thank you.